So this is example 5.2.2 out of your book. We're going to do it so that we can talk about problem 5.9. In this example, a bicycle wheel of radius b. So here's my wheel, and it's got a radius of b, and it's rolling at speed v0 around a big circle that's got radius rho. So it's just rolling in a circle, kind of like that. And they're asking us, what's the acceleration of the highest point on the wheel? That's this point on top of the wheel in the inertial frame, right? And so this is our equation for acceleration. Its acceleration is the acceleration in the prime frame plus omega dot cross r prime, which is the tangential acceleration, plus the Coriolis term, plus the centripetal term, plus the relative acceleration of the two frames. Now when we pick a frame for this, we don't want to pick a frame that's rotating too much, and so what we're going to do is pick the frame attached to the center of the wheel, but not also turning with the wheel. This frame is just going to go around with the wheel, so the wheel in our prime frame, the wheel will be spinning in the y prime z prime frame, and the x prime axis will always point in the direction of the center of the circle, and so it's going to go around like this, basically. And so the omega in all of these, in these equations, is the angular velocity of this frame about the circle, or just v0 over rho. v0 is the speed of the wheel, and rho is the radius of the circle it's going around. So if I divide v0 by rho, I get the angular velocity. Notice it points up. The angular velocity points up, and so its direction is k hat prime. And so that's the omega used in all of these. V prime is the speed of the point we're interested in, which is the top of the circle, in the prime frame. And so notice in the prime frame the wheel is spinning, right? The frame is fixed, and C prime always points up, but the wheel is spinning. The speed of the top of the wheel in the prime frame is just v0, and it's in the minus j hat direction because the top of the wheel is going this way, the top of the wheel is going that way, with speed v0 in the prime frame. R prime is just the position of the top of the wheel, and that's just b times k hat prime, because b is the radius of the wheel. And finally, the acceleration in the prime frame, in this frame, the wheel is just spinning about the center, right? And so it's spinning in the y prime z prime plane, and so the acceleration in the prime frame is just v squared over r, right? In this case, it's v naught squared. That's the speed in the prime frame divided by the radius of the wheel, and then it's towards the center, so it's in the minus k hat prime direction. And so we're going to have to work out all of these terms, but we've defined these guys. A0 is the acceleration of this object. Is the acceleration of the frame, of the rotating frame relative to the inertial frame. So if you want to say it's the acceleration of the origin in this frame relative to the origin here, and that's just going to be a v squared over r. In this case, it's going to be a v naught squared over b in the I hat direction, I hat prime direction. All right, so I'm going to work all those out here in a second. So here we are with our example again. So I've rewritten, here's the diagram we're in again. I've rewritten the acceleration out here, and based on the terms we looked at in the previous screen, the acceleration of this point in the prime frame, it's just spinning around this way, and so it's the top point has a centripetal acceleration downward in the prime frame, and so it's just minus v squared over b. Again, b is the radius of the wheel times k hat prime. We're looking at the top point, so it's downward. The tangential acceleration, the transverse acceleration, is 0 because omega is not changing. It's just rolling at a constant speed v0, and so this guy goes away. The Coriolis term is just 2 omega cross v in the prime frame. Well, omega is the omega of the frame, and so it's the angular velocity of the wheel going around the track, and so that's v0 over rho, where rho is the radius of the track. And since it's this way, it's k hat prime, like we said on the previous screen, cross the velocity in the prime frame. The velocity of this point in the prime frame is minus v0 j hat prime. It's going this way, and its speed in the prime frame is v0. In the unprime frame, the top of the wheel is going at speed 2v0, this way. But in the prime frame, it's just spinning on its axis with speed v0. All right. And so that gives me the Coriolis term. The centripetal acceleration of this point is the angular velocity of the frame, omega cross r, but they're all k-hats. The position is k-hat, and so these two guys produce a 0, and so this just gives me a big 0 here. And then I also have to include the acceleration of the frame, because my rotating frame, it's no longer coaxial like we did in these other problems. My frame is now accelerating relative to the unprimed frame. And so I have to include that, and its acceleration is another centripetal acceleration. It's v squared over rho. And since it's accelerating towards the center as the wheel goes around, the wheel could have been going in a straight line, but it's not. It's going in a circle. And so it's accelerating with this acceleration because it's accelerating towards the center, and that's the I hat prime direction. And so I have, I think, three terms. This term, and this term that aren't 0. And so those are all here. This gives me v naught squared over b times k hat with a minus because it's accelerating downward. And these two gives me 2 in the I hat direction. And notice they have the same v and rho in there. And so my total acceleration comes out to minus v naught squared over b k hat prime plus 3 v naught squared over rho I hat prime. And that's example 22. 2.2. 5.2.2.